Hello everyone, my name is Jamal Ahmadi alongside with Saro Karami. We are doing presentation our project for advanced power system, which is ENGI 9858 under supervision of Dr. Ashraf Ali Khan for 2025 2026 fall semester, which is a hybrid renewable energy system design and simulation for a remote area in Newfoundland and Labrador. We did a hybrid power system for a remote area, which is common for northern Canadian territories. In continuous, my friend Saro, which will go ahead with presenting the rest of the project. Thank you for watching.
Around the world, people are working toward using energy without causing pollution. That's why renewable energy like wind, solar, and hydro is so important. But these energy sources don't always give power when we need it. So we use hybrid systems that combine them with batteries and backup power. In this study, I focused on Bell Island, which has strong wind but a weak connection to the main power grid. I used Homer Pro to find the best mix of wind, solar, batteries, and the grid to keep power cheap and reliable. I also used MATLAB Simulating to study how the system reacts to changes like wind speed. The results show that this type of system can really help reduce costs, cut carbon emissions, and improve energy reliability. Energy is essential for everyone's life and for growing the economy, but it also causes most of the greenhouse gases that lead to climate change, about 78% globally, and even more in Canada, because of our cold climate and long distances between towns. Many small Canadian communities like Bell Island still use diesel generators, which are very expensive and bad for the environment. Solar and wind energy are cleaner, but they don't always work when we need them, like when the sun isn't shining or when the wind isn't blowing. That's why we need hybrid systems that combine different energy sources with batteries and smart controls. Most older studies only looked at parts of the problem, but this project takes a complete view, looking at both the costs and how the system behaves in real conditions. This project has five main goals. The first goal is designing a hybrid system that works well in Bell Island's weather and energy conditions. The next goal is using Homer Pro to test different combinations of wind, solar, batteries, and the power grid and choose the most cost effective one. The third one is using Canadian made equipment as much as possible. This supports local jobs and makes future maintenance easier. The fourth one is using MATLAB Simulink to test how the system performs when wind speed or grid voltage changes quickly. To measure both economic results like cost per kilowatt hour and how long until we earn the money back, and environmental results such as how much CO2 we can cut over 25 years will be our fifth goal. To build a reliable model, we first needed good data. We used electricity usage data from Statistics Canada and local utilities to understand how much power people use during different times of the day and year. For wind and solar, we used weather data from Environment Canada over the last 10 years. The wind turbines we chose are EO20 and EOX M21 are proven to work well in Canada. For solar, we selected Canadian solar panels. Battery sizes were based on how much backup power was needed during times with low wind or sun. For the financial part, we used realistic numbers of inflation, interest, and fuel prices, and we planned the system for 25 years, including parts replacement. The island has around 2,079 people, most of them living in Vabana. Most homes are single detached houses and they use more energy than apartments or smaller homes. Based on average use in cold climates, we estimated that the island needs about 13.4 million kilowatt hours of electricity per year. The highest power demand, called peak load, is about 4,552 kilowatts in winter when heating is needed most. Knowing these numbers helped us figure out how big the system needed to be to meet the demand. Wind on the island is pretty strong, averaging 6 to 8 meters per second, and it's even stronger in winter. That makes wind a good energy source. Solar power is better in summer when there is more daylight. This means that the system needs to balance both sources across seasons. We use this information to decide how much battery storage we needed so that power is still available at night or during calm days. The final system design includes 178 EO20 wind turbines and 28 EOX M21 turbines. Together, they generate around 23.6 million kilowatt hours a year. The system also connects to the grid, which acts as backup and allows us to sell extra power back. This is called net metering. The battery system stores power during high production times and releases it when needed. We included redundancy and peak load matching so the system works even during tough conditions. A diagram shows how everything connects and works together. The total startup cost is about $2.55 million, dollars, which includes the turbines, solar panels, batteries, and installations. But the annual operating costs are low, only about $380,000, which is much less than diesel systems. The cost per kilowatt hour is about 1.95 cents compared to 13.2 from the regular grid, a huge saving. The base system would produce 322,000 kilograms of CO2 every year. Our new system actually removes 243,000 kilograms of CO2 per year because of clean energy and selling power back. The project pays for itself in under 2 years, and the return on investment is about 55.5%, which is excellent. The money made from selling extra power helps cover yearly costs. We built a detailed model in MATLAB Simulink to simulate how this wind system works, especially under real conditions. We used a special type of wind turbine called DFIG, which lets us control things like rotor speed and voltage. The system is split into two groups based on turbine size, and this helps us accurately predict how much power the whole wind farm will produce. DFIG turbines are very flexible. They let us change the rotor speed to get the most energy from the wind. This is called MPPT. They also control reactive power, which helps keep the grid stable. In voltage regulation mode, the turbine keeps voltage at safe levels. In VAR regulation mode, it adjusts reactive power flow to improve grid quality. These controls act very quickly, within milliseconds, so the system can handle sudden changes in wind or grid conditions. Here we have the dynamic simulation, wind speed step response. We ran a test where wind speed suddenly increased from 8 to 14 meters per second. The turbine automatically changed its blade angle to avoid overload. The power output went up, but there was a small overshoot due to system lag. Reactive power also changed to keep the voltage stable. These tests showed that the system can handle fast changes in wind speed safely and effectively. As you can see here, we have the dynamic simulation voltage sag compensation. In another test, we simulated a short voltage drop or sag on the grid. It lasted just 0.5 seconds, but the turbines reacted immediately by injecting more reactive power. This quickly brought the voltage back to normal. This shows that the system can not only generate electricity but also helps support the grid and improve its stability. To sum up, our system provides over 90% of the electricity from renewable sources. It saves money and pays back the investment quickly. It helps fight climate change by cutting or even reversing emissions. It works well under real world conditions as proven by the dynamic simulations. It also uses Canadian made parts which supports local jobs and improves reliability. Of course, we did see some challenges like battery wear over time and possible grid upgrade needs, which we suggest for future work. In conclusion, this hybrid system is a great solution for remote places like Bell Island. It's clean, cost effective, and works well with the grid. The design we used can be copied in other similar locations in Canada or even worldwide. In the future, we plan to study better battery technologies, larger storage, and smarter controls that can predict changes. Keeping the system monitoring and making updates over time will make sure it works well for many years. Thank you all for listening. I hope this presentation gave you a clear idea of how hybrid renewable systems can help communities like Bell Island. I would be happy to answer any questions you may have. Have a good one.